This is derivatives part 2. In the first part, we defined what a derivative was. This time, I'm just going to go through some common derivatives that we'll run across in the class and other classes as well. So last time, we started with y equals mx plus b. And the derivative of that, dy dx, that's the derivative of y with respect to x, is the slope m. Now, if we had another function, another polynomial, maybe we had y equals ax squared. That derivative is dy dx equals 2ax. So what happened was that exponent 2 came out in front here, and then instead of x to the squared here, we actually have x to the first power. So we can keep on going. You could have y equals something like bx cubed, and then dy dx would be 3b times x squared. And we can generalize that as equaling y, say, cx to the nth power. Dy dx in that case is n times c x n minus 1. So that's x to the n minus 1 power. And that'll work for all of these. And then there's actually an even simpler one that we didn't include. What happens if y just equals a constant b? Then dy dx in that case equals 0. We can combine these functions and still take the derivative. I could write y equals, say, mx plus ax squared plus bx cubed. And when I'm doing this, all I have to do is take the derivative of each term. So dy dx here equals m plus 2a x plus 3b x squared. And we can do this for more and more complicated functions. Another type of function that comes up a lot is the exponential. So if we had y equals e to the x, then dy dx is actually e to the x. So this is actually one of the attributes of an exponential function, is that its derivative is the same as the function itself. So every value on an exponential curve is the slope of that curve. And we should make that a little more general. We could put a times e to the bx. And then if we take dy dx, it's just b times a e to the e to the bx. We can make this more complicated. Y equals a e to the bx squared. And when we're doing this, what really happens is we're going to use something called the chain rule. So we're going to take the derivative of the main function, and then we'll take the derivative of what's inside it too. So dy dx here, it's really ae bx squared, but then times the derivative of what's up here too, which is, from the last slide, something like 2bx. And so if we rewrite that more cleanly, then we have 2ba x e to the bx squared. One related function that comes up is the natural log. So if we have y equals log base e of x, then that derivative is actually dy dx equals 1 over x. And another way to write that that's often seen is ln x. And that's the same derivative. I hope this helped your math.